And this stuff is applications of trig functions, so modeling, but it's really word problems applications using trig functions to solve sort of real world problems. There's a few different kinds of applications, very common applications that we see, and like these are sort of day-to-day kind of things. So the one that we're going to look at is tides. What are tides? Who can explain what tides are? Yeah, they have that kind of a curve. Something happens with the moon? Yep, the moon does cause the tides. Yep. Yeah, like so oceans and seas and some very large lakes. Most lakes aren't big enough, I think, for it to be noticeable, but the depth changes. So one thing that I realize is they must just pick a spot to measure, because like it says in this question that it ranges from 0.8 feet to 6.4 feet. But if you go further out, it's going to be deeper. So I guess they just pick some spot where they measure consistently, and throughout the course of a day, it gets deeper and less deep, right? And that's what the tide is. And this is relevant if you want to swim. You might not want the tides to be too deep. They're going to be a bit dangerous, a bit more dangerous maybe. The waves are a bit bigger. I'm not sure if that's true. But if you are surfing, then you want to surf usually at high tide, right? So, this is something that people do. And if you've ever been to like some kind of oceanside resort, they will often post the times that the tides are going to be high and low for people to be able to swim or surf or whatever, or just to know. Have you, or how many people have like gone to the ocean and sort of been around and noticed the tides? Have people done that? And have you ever explored tide pools? You know what that is? Yeah? So a tide pool, like, obviously it depends on the beach, but if you have a beach that's very rocky, so I actually spent time in Durban in South Africa, and the beach that we were close to had big, like sort of rock surfaces, right? So not great for swimming, but when the tide goes out, when the tide gets lower, you've got these rocks that catch water in them, right? Because the water goes out, and it catches like wildlife, fish. We would find octopus in the little tide pools, and you could just kind of walk around and explore an area that 3 hours ago was underwater, and now it's not underwater. It's really kind of interesting. So anyway, that's what the tide is. So that's one of the sort of two applications we're going to focus on. The other one that we're going to that you'll see in the practice is Ferris wheels. But there are other applications. Can you think of other things in the world that kind of go up and down on a regular or regular-ish kind of basis? What other things? What other kinds of applications? Huh? Airplanes. I could imagine an airplane that goes up and then back down and lands, but then would kind of stay there for a little while, but then maybe does the same route the other direction, something like that. Could be. I don't think they would follow a perfect sinusoidal curve, but they do go up and down, that's for sure. Anybody think of anything else? No? Yeah? Levels of? Level of the land close to an ocean, yes, would, because it would follow the same kind of relationship as the tide, just the other way around kind of thing. Yep. No other ideas? Yep. A roller coaster could. You could build a roller coaster that does. What's the roller coaster? It's not a roller coaster, but what's the ride at Canada's Wonderland that just drops straight down? Huh? Yeah, I can't remember the name of it, something like that. If it went up and down on a very regular basis, which it kind of does, that would follow a sinusoidal curve for sure. Sunlight throughout the course of the year, that does, right? So in the summer, there are more hours of sunlight for us, and in the winter, there are fewer hours of sunlight. And that follows a very, very nice sinusoidal curve. And you can find that data online. And if you got that and put it into a spreadsheet and graphed it, like it would look really, really nice. What happens to the sunlight in like the Yukon throughout the year? Or Alaska, way up north?
I don't know if this is true, but I don't think it's that.
It's exactly true. You're exactly right. So there are times in their sort of summer season where the sun doesn't set. It's just sunny all the time. Now, it would still go up higher in the sky and lower, but it never goes below the horizon. So it's sunny all the time. And then on the other half of the year, or on the other side of the year, it goes down for like 2 weeks and it's just dark and it never comes up. The sun doesn't rise for a couple of weeks, kind of thing. It would be very strange, obviously, to experience that and live for 2 weeks just in the dark. But every year, you know, people who live there, they're used to it, and that's just what happens. So that's a change in amplitude, isn't it? Right? So they go from 24 hours of sunlight to 0. So that's a huge change or difference in from the max to the min. So that's a change in amplitude. What do we go from? Like 14 hours to 16 hours or so, or maybe it's more than that, but you know, like it's nowhere near that big of a change. Maybe it's like 12 hours or so at the lowest, I don't know, but right. So around here, the difference, it really doesn't fluctuate that much, right? So that's a difference in amplitude, and that's a lot of what this kind of modeling is about, is thinking about how the real world events, how they relate to the properties of a sinusoidal function. We're not going to explore. There is a question in the extra practice on hours of sunlight, but it's a little bit trickier of a question, so we're not going to explore that too much. But if we have more time, that's probably what we would do because it's interesting. So we're going to stick with sort of, or the main ones that you have to be aware of are the tides and the Ferris wheels. Before we move on to the lesson, I just want to take a look at a Ferris wheel. So imagine this is a Ferris wheel, okay? And you probably get on at the bottom. I don't know that I've ever seen a Ferris wheel where you get on like at the top, but I suppose you could have one on the side of a cliff or something. That'd be interesting, but generally you get on at the bottom. And obviously that's what you do if you're watching the black dot is like a rider, and you go up and then you go back down and then you go back up and then back down. Okay? And so how is that modeled by a sinusoidal curve? Well, over time, you go up to the max, back down to the min. This one takes a minute to go from the bottom all the way around back to the bottom. Back up to the max, back down to the min. So it's a perfect, looks like a cosine curve because we are thinking that we're starting at a min, right? And so this is the kind of thing that you're going to have to be thinking about if I change. So this one has a height, the blue one has a height of 32. The red one has a height of 16. What does that change in the graph and in the equation? Oh, and this one let's make these equal. So the speed of one just means it takes 1 minute. So these two have the same period, but a different max height, so a different amplitude, and a different zero line, right? But same period. I could make this one faster. Smaller ones probably do tend to go faster. So that's a change in the period. It takes less time to go all the way around. Now the red one's going around in 30 seconds as opposed to in a minute. So it can complete 2 full cycles. So it's got a shorter period, so that's impacting the K value. right? And so that's the kind of thing that we're thinking about. Again, though, notice like in the last lesson, generally speaking, we're starting at a minimum, or in some cases for the tide questions, you might start at a max. So we're probably talking about cosine as the easiest equation to model these with. Yes, you could figure out what the phase shift is to start on the zero line and make it a sine curve. It's just more work. I don't know why you would, right? Okay, so let's get into it. The tide off the coast of Durban, South Africa ranges from 0.8 feet to 6.4 feet about 6 hours later, and repeats this cycle once every 12 hours. If you take out all the extra words, this question is a lot like the first question that we did in the last lesson, where it gives us a max and a min and the period, and we have to come up with the equation, right? Now we're going to do some other things. We're going to sketch this. We are going to determine the equation, and we're going to use the equation and think about a couple other things about this relationship. But this lesson or these problems are a lot like the problems you were just working on, but they just have words attached to them. Okay? So it's very much the same idea. So the first thing we're going to do is make a sketch of the relation over 24 hours. So if this is over 24 hours, how many times are we going to, or how many cycles are we going to see? 2 cycles, right? One cycle happens every 12 hours, but we're graphing 24 hours. So we'll have 2 cycles. Very good. So when we sketch, kind of like what we've done in the past, it's going to be important how we label things. Okay, so we got to draw out our axes and then label everything nicely. So I'm going to call this D for depth. Sometimes we just say H instead for height. It doesn't really matter. Generally speaking, we do use letters other than X and Y when we're doing applications. We try to pick letters that kind of go along with what they represent, right? So this is going to be time in hours. So we'll call it T. Now I do kind of want this to be not to scale, but to some extent look like a proper curve. So what I like to do is kind of use my ruler and just sort of get a few points. Okay. Because otherwise, when you go to draw the curve, if you don't really have anything to follow, it can just kind of be hard to make it look nice. Okay, so we're going to start at the minimum. Here's going to be my max. So this is 0.8 feet, and this is 6.4. So I'm just kind of giving myself a little bit of a, I don't know, spot to aim for, I guess you might say. Okay. So this is 12 hours. 24. This is 6 hours. 18 hours. So I've sort of labeled my axis with the max and the min, and labeled like on the vertical axis, and then horizontally sort of labeled every 6 hours, because that's when a max happens, when a min happens. You could label, I could go further and do every 3, but this is good enough. But you do need to label some scale along both axes kind of thing. Okay. Definitely have to use a ruler when you're drawing your axes. And like I said, try to make the curve look kind of symmetrical, kind of balanced, that kind of thing. But it's not a graph. It's just a sketch. Everybody good? So that was part A. Part B. Determine an equation for this relation. So we just talked about this. When we're asked to do an equation, what should our focus be? How do we frame this in an easier way? Exactly. Our goal is to find A, K, C, and D. Order doesn't matter which order you do it in, but that's what gives you focus. Once we have those 4 values, then we can write the equation. What jumps out at you to start with? What do you think? C is 0. Nice. I like the easy ones. We're going to start at a min. Why not? And often, again, with these applications, they start at 0, so your C value is going to be 0. What else?
Would D be 0.8? Wait, no. It would be in between.
Ah, very good. So we can find the midpoint between 0.8 and 6.4. Like I said before, sometimes what people like to do is find the amplitude and then use, I don't know why, I think a lot of people just, that sticks for them more, finding the amplitude, which is max minus min divided by 2, and then use that to find the D value or the 0 line, but you could do it the other way around. What were you going to say? Abdullah? No? Oh, I thought you had your hand up. Okay, so let's say we want to find the amplitude. It's 6.4 minus 0.8 divided by 2. What does that give us? Anybody with a calculator? 2.8. Therefore, what is A? Jasper? Thank you very much. Negative 2.8. Right? Because we're starting at a min, so we have to reflect it. Okay. And so the last lesson we did the D value a different way. So this time, how about we do it like this? A lot of people like to think of it like this. 6.4 minus 2.8. The minus has nothing to do with the negative A value. I'm going from the max down the amplitude to get to the 0 line, right? And so what does that work out to? 3.6. The other way, like we talked about before, is add the max and the min and divide by 2. Okay. I like to mark the 0 line on my graph. I just think that it kind of helps sort of visualizing the whole thing, but it's not required. Okay, what are we missing? We've got A, we've got C, we've got D. We're missing K. How do we find it? It's not different from before.
The number of hours it takes for one cycle?
Is the period. So how do we find the K value?
Is it 2 pi divided by 1?
Yeah, it is still 2 pi divided by the period. So 2 pi over 12. which works out to pi by 6. So often in these applications, our period will be written in terms of pi, which we haven't seen before. But that's because before, our k value, if we were graphing, we were just given a k value of 2 or a half. Like we weren't given a k value in terms of pi. But these ones are like 12 hours for it to repeat, right? You don't have a cycle of pi. You have a cycle of, or a period length of 12 or something like that. So the k value will often have a pi in it. Okay, and I think we have everything. And again, we usually do function notation for these just because that's the way we do it. Negative 2.8 cos pi by 6t plus 3.6. Question C, what is the depth 2 hours from low tide? So the fact that we started our graph at low tide and our equation starts at low tide is going to make that easy. I don't believe, this question didn't say we had to sketch starting at low tide, so I chose to do that. We could have started at high tide. I think in the practice, one of the questions says starting from low tide or high tide. I can't remember which one it says, and then the other one just doesn't, so you kind of get to choose. But because question C says, what is the depth 2 hours from low tide? Well, our equation is already set up for that. If we had done our equation starting at high tide, we would have kind of had to think about it a little bit to figure out what 2 hours after low tide would be. Okay, so it's something to be mindful of. So how do I do question C? Yeah, so just at t equals 2 or d at 2. Pi by 6 times 2 is 2 pi by 6, which is pi by 3. So we could actually do that in our head. Some of it, right? Actually, all of this would be not too hard to do in your head. But you're going to do this on your calculator. Be aware there is there's some calculators, if you use brackets to multiply in this situation, it might actually give you the wrong answer. So I would recommend trying this on your calculator and make sure you get the right answer. What I'm going to do, if you want to watch, is negative 2.8 cos of 2 pi divided by 6. So I just like to take the t value, put it in front. It's quicker to type. The mistake happens when you do this on some calculators. It interprets bedmass differently from how you intended it. So to me, typing it in this way avoids all issues. It's also a little bit faster. Plus 3.6. So you should get 2.2. So make sure that you can type it in and get 2.2. If you get something else, ask me about it after, and we'll make sure that you know how to. Also, you have to be in radians, of course. So if you had physics and you had your calculator back in degrees, put it back in radians. Everybody good? Last question, how many times a day is the depth? Exactly 6. So, we sketched it thinking about the properties, thinking about the max and the min, but having that sketch, I think, helps us come up with the equation, right? Helps us kind of visualize and think about where the A, the D, and the C and everything, like when you have the sketch, you look at it and you say, oh, C is 0. I'm starting at a min. Like that's an easy thing to think about, right? So it helps. But then also for a question like, the other thing it helps with is at t equals 2, where's 2? Right around here somewhere? Does the answer of 2.2 make sense? Sure, I think so. I mean, you can't say exactly. If I had put it in my calculator and got an answer of like 0.9, I'd probably say, well, wait a minute, that doesn't look right. Shouldn't it be a lot higher than that by then? Or if I got an answer of 5 point something, I'd be like, no, that can't be right. It's definitely not way up there, right? So you can kind of estimate and make some sense of whether your answer is reasonable. Also, if the question was 2 hours after high tide, you can use the graph to think about what you would put into the equation, right? What would you have to sub in to the equation? Because my equation starts at low tide, but if it's 2 hours after high tide, like how many hours after low tide would that be, right? So it can help you visualize. It's also going to help us answer this last question. How many times a day is the depth exactly 6 feet? And maybe 6 feet is where it's deep enough to go surfing or something, so you kind of not want to know about what time of day it would be safe or not. Yeah, Jasper.
4 times.
4 times. So, somewhere here, 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 and here, something like that, at like 6 feet, right? So 4 times.